Welcome back, everyone. Let's finish up chapter 10, shall we? And finish up our discussion of the structure and reactivity of some derivatives of carboxylic acids. We have a few more things to say about esters and amides, and then I think that will be the proverbial that. So we ended last time talking about how esters can be hydrolyzed in either acid or base. Basic hydrolysis of esters, of course, is also called saponification. So there you go again, two names for the exact same thing. Organic chemists just love that for some reason. But in any case, not only can you treat esters with water, you can also treat it with ammonia. Or in fact, it doesn't even have to be ammonia. Your book uses ammonia, but this could also be actually any primary or secondary amine. There does need to be at least one H attached to the nitrogen, but the other two bonds can be to either carbons or hydrogens, doesn't matter which. In the end, if you treat an ester with either ammonia or, again, a primary or secondary amine, I wouldn't be shocked if this required some heat as well. The conditions, to me, really are neither particularly acidic nor particularly alkaline. It's probably fairly close to pH 7, actually. In any case, the end product is an amide of this type. And the other portion of the ester winds up in a molecule of an alcohol. Almost certainly that will be a molecule of methanol or ethanol, and that will just wind up in the waste jug. But the major organic product will be the amide. So, as always, especially with OWL, look carefully to see what they're asking about. If they want you to draw both products, then do so, but certainly the major organic product, the one of interest, is going to be the amide. And a good rule of thumb for that, by the way, if you're ever wondering what you have to put down as being the major product, I'm sure there's exceptions, but the chances are at least 90% it's going to be the biggest possible molecule there. I can think of a small handful of exceptions, but I don't know that we'll be running into those. So the major product is this amide. And again, had we used ammonia, then this would be NH2 over here. It'd be a primary amide. But the concept and mechanism behind this reaction is just like saponification of esters, except instead of water, we're using an amine. So just to give an example, here we have methyl benzoate. If we treated this, if we heated this, let's say, in the presence of butylamine, which I just picked because I felt like it, then I'd expect that you would get this butanamide shown here. And if instead of butylamine, we just used ammonia, NH3, well, then you just get the primary amide, benzamide. So, but other than that, conceptually, this is no different than hydrolysis of esters. We're just replacing the oxygen of water with the nitrogen of either ammonia or a primary or secondary amine. Other than that, it's identical. One other reaction of esters that we should talk about is the reduction of esters with our old friend from the previous chapter, lithium aluminum hydride. And lithium aluminum hydride will reduce any ester to the corresponding primary alcohol. So it reduces it all the way down. The carbonyl carbon becomes a CH2 in the product. And then you will also get a molecule of almost certainly either methanol or ethanol. And that's water soluble. That's going to wind up in the waste jug after the inevitable aqueous workup. One thing that I don't think your book mentioned, possibly I missed it, but I should also let you know the same is true for carboxylic acids. They can also be reduced by lithium aluminum hydride. And again, you will get the primary alcohol. In this case, I believe the fate of the other oxygen is to wind up in a molecule of water. But of course, we're focusing on the major organic product. And the reaction is quite general. The group R1, or R in this case, can be pretty much anything. One thing that your book also does not mention, but is a serious omission on its part, is that whereas lithium aluminum hydride will react with esters and carboxylic acids to do the reduction, sodium borohydride will not touch either esters or carboxylic acids. Back in the previous chapter, you may recall, we said that for ketones and aldehydes, sodium borohydride and lithium aluminum hydride are interchangeable reagents. either of them will reduce a ketone to a secondary alcohol or an aldehyde to a primary alcohol. That's not true for esters or carboxylic acids. Those two reagents are not interchangeable. Only LAH, only lithium aluminum hydride, will reduce an ester or carboxylic acid. That's because esters and carboxylic acids, again, as we mentioned earlier, are very much near the bottom of the reactivity scale of acyl derivatives, and certainly also less reactive, other things being equal, than aldehydes and ketones. And we gave some reasons for why that is. So you do need to use LAH. Sodium borohydride will not touch a carboxylic acid or an ester. The two reagents, while interchangeable for aldehydes and ketones, are not interchangeable for esters and carboxylic acids. There you must use LAH if you want to reduce them. What that means is we have something that we can take advantage of. Let's say we had a molecule, something like this one down here, which, as you can see, has both a ketone and an ester functional group. We can distinguish between the reactivity of those two groups depending on which product we want to make by choosing one of these reagents. If we reacted this keto ester, we would call it, with LAH, it would reduce both functional groups. It'll reduce the ketone to a secondary alcohol and the ester to a primary alcohol. Of course, methanol is the side product here. Whereas if we treated this compound with sodium borohydride will not touch this ester. That will remain unreacted, but it will still reduce the ketone to a secondary alcohol. And I think that's a serious omission in the part of your book. Otherwise, why even mention both reagents? There's no point. You're learning about both of them. They might as well have just told you use always LAH, and then that would have been the end of it. But since they mention both reagents in chapter 9, I feel it's my job to tell you the rest of the truth and kind of draw this loop closed here, so to speak. So much then for esters. Last acyl derivative we should cover, and we've already mentioned a lot about them, is amides. Amides are, of course, the amino derivative of carboxylic acids. They're quite similar to esters, though I would have to give the edge to esters in terms of being a little bit more reactive. So amides react a little bit more slowly than esters. Amides can still be hydrolyzed, just like esters can, under either acidic or alkaline conditions. And just like with esters, just like with nitriles, the major organic product will be the corresponding carboxylic acid. In the case of amides, just like with nitriles, you recall with nitriles, the nitrogen in the nitrile winds up in a molecule of ammonia. So the amino group part of an ester winds up in a molecule of either ammonia or a primary or secondary amine, depending on what else is attached to the nitrogen. But we're not really as concerned about that part. We want to focus on the major organic product, as we always do, and that's going to be the carboxylic acid, just like for esters, just like for nitriles. And I should also mention, your book points out correctly that cyclic esters are a thing. They're called lactones. I would also have you know that cyclic amides are also possible, and they are called lactams. I don't know if you're ever going to run into them. These things do show up, though. There's a number of important drugs, I think mainly some antibiotics, but you'll need to check me on that contain lactam functional groups, that contain cyclic amides. And finally, we've already covered the order of reactivity from carboxylic acids at the low reactivity end all the way up to acid chlorides at the other end. And that's why acid chlorides or anhydrides are the reagent of choice. They'll react with pretty much anything. And we've spoken a little bit about the reactions of acid chlorides and acid anhydrides. We touched on that in the chapter in carbohydrates, when we said that you can make you can exhaustively acylate a sugar molecule and make esters out of all the OH groups. That's done by using the corresponding acid chloride or acid anhydride. So those are going to be the reagents of choice, one of those two, because they're most reactive, and they'll react with anything. Conceptually, the reaction is no different from anything else we've covered in this chapter. But the last section of this chapter is a nice summary of all of these things, so you might want to take a look. So we covered that already. You might find the format that the book gives the information in to be more helpful. Whichever you prefer is totally fine with me. Other than that, that's all for chapter 10, and with it, that's all for the material for exam number 4, not the final exam, but our last hour exam. We still need to cover chapter 17, which is on proteins and polypeptides. Again, we're going to focus on looking at and understanding those compounds from the perspective of an organic chemist. We're going to shy away from biological activity. I don't think that's appropriate for this course. But we will also cover those. That material will not be on the 4th hour exam. It will be fair game for the final exam, but it will not be on exam number 4, on our exam number 4. I mention that because I'm thinking actually of producing that video before we take our 4th hour exam, and that will be officially it for the class material. So other than that, I hope you're all staying safe and healthy, and see you next time.